Alrighty, today we are going to finish going over 5.2. Remember yesterday in the video, we talked about these 3 rules for writing electron diagrams and longhand and shorthand, for writing electron configurations, okay? So we have these 3 rules. We have the Aufbau principle. I have some arrows on there. The Aufbau principle. And remember, this tells us that electrons occupy orbitals with the lowest energy levels first. And I have this nice diagram that I think is going to be very useful for you while you're learning this and doing your homework and everything. Remember that our 1s has the lowest energy, 2s has the next, 2p, and up. The only place it really gets confusing here is with the 4s and the 3d, and then with the 5s and the 4d. So we're going to find that we don't have any D sublevels down here, but I'm going to explain all of this today. But when we do get to them, I'm going to actually make myself a note to come back to this, because it will make more sense once I show you on the periodic table what's going on with that. Okay, so just remember, the electrons fill the lowest energy levels first, so they would go to the 1s, then the 2s, the 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then F. That is just a mess. The F, we're just ignoring that. You don't even have to think about that one. Just ignore the F, 4F there. Then we go 4d and then 6p. All right, so we are going to apply this principle today when we actually start really writing our electron diagrams. Next, we have the Pauli exclusion principle, and remember that tells us that only 2 electrons, the maximum is 2 electrons per orbital. I could have 1 electron, but the maximum I can have is 2. I can't have 3 in an orbital. And remember, we defined the orbital yesterday as the square, right? So an S sublevel has 1 orbital. A P sublevel has 1, 2, 3 orbitals, and a D sublevel has 1, 2, 3, 4. I'm not gonna fit 5. Okay, 5. Right, that's the D sublevel. So we have each little square is 1 orbital, and each orbital can hold 2 electrons. And the second part of Pauli exclusion principle states that we must have the electrons must be have opposite spin. Remember that word spin? Spin means that one arrow must be pointing up, one arrow must be pointing down. The up arrow indicates a clockwise orbit, electron orbit, and the down arrow indicates a counterclockwise electron orbit. Finally, we finished with Hund's rule, and I explained that to you, that Hund's rule says that electrons occupy orbitals in a way to maximize the number of electrons that have the same direction of spin. So this rule can be tricky, and it's going to make much more sense once I start actually doing all of the electron configurations for you and showing you what I mean by that. So I told you we were going to talk about, this is where I stopped. We're going to talk about the stability of each of these, and I'm going to do all of the electron configurations. Then we're going to come back and we're going to look at this, and we're going to look at why the 3D orbital has more energy, or the 3D sublevel has more energy than the 4s, why the 4D has more than the 5s, etc., etc. So we're going to put a pin in it, as they say, and we're going to come back to those things. So really quickly, remember yesterday I also told you there are 3 ways that we can write electron configurations. We can do diagrams, we can write them longhand, and we can write them shorthand. So today we're going to look at the periodic table, and we're going to write our electron diagrams we're going to write our electron configurations. We're going to write the diagram, we're going to write the longhand, and we're going to write the shorthand. So what I'm going to do is I'm going to go through, and I'm going to be talking about the 3 rules as I write as I write these 3. So if it doesn't immediately make sense, don't give up. Please watch until I get to fluorine, and then if it doesn't make sense, you can ask me questions. But please watch, because you're gonna see the pattern, as I go through this, and it's going to make sense as you watch me make the diagrams longhand and shorthands, okay? So let's start with hydrogen. Hydrogen is number 1 here on the periodic table. I know that's tiny, but I need room. I can make it a little bigger, I guess, for right now. So, we only really need the top. We don't need the bottom. Okay, so hydrogen is number 1 here, right? Whoops, right here. So that means it has 1 electron. So the purpose of the electron configuration is to say where exactly in space around the nucleus does this electron exist. Where does this electron exist? So we're going to use our 3 rules. First, Aufbau's principle. Number 1, remember it says that the electrons are going to occupy the lowest energy level first. So if I have 1 electron, I'm not going to just randomly put it in the 6s sublevel. No. I'm going to always start in the 1s, then I'll go to the 2s, etc., etc. Hydrogen has 1 electron. Therefore, I will start with... This is how I draw the diagram, okay? So I'm going to write, 1s here, and I have 1 electron. Remember, because of Hund's rule, the second component of Hund's rule was we want them, we place the upward facing arrows first. So I have to put the clockwise arrow in first. That is my 1 electron. Remember, 1 arrow signifies 1 electron. So I have 1 electron. What does this, I forgot to write for my electron diagram. There. Now my electron diagram, that is the complete electron diagram. I have the orbital drawn. I have the electron drawn as an up arrow, and then I have the description written here. 1 means n equals 1. S means I'm in the S sublevel, and this little 1 up here in the superscript means that it's called a superscript, right? Yeah. Subscript is below, superscript is above. Yes, that's a superscript. That means I have 1 electron in this orbital. Okay, so at the first energy level, in the S sublevel, and 1 electron, and it's drawn here as an up arrow, meaning that the electron is spinning around the nucleus in a spherical S pattern in the clockwise direction. Okay, so that is how this is super. This is super complex, but it's also like pretty easy to understand. This is just telling us exactly where the electron is. The longhand is very simple because if you can do the diagram, you can do the longhand no problem. The longhand is just writing, no drawing, and it's just literally writing the description here, right? So the longhand, we don't have to draw where the electrons are, we just have to write like this. And from this longhand, again, I can say, okay, I'm in the first energy level, I'm in the S sublevel, and I have 1 electron, right? So that's what all those numbers tell us. And finally, for our shorthand, for the first 2 elements on the periodic table, so for hydrogen and helium, we actually don't have a shorthand. So hydrogen and helium don't have shorthands, so we're not going to get there yet. All right, so that's how you write the diagram and the longhand. Now let's look at helium. So helium is number 2 on the periodic table, and it has 2 electrons. So because of Aufbau's principle, we have to start at the lowest energy level, which is 1s. All right, I have 2 electrons. The nice thing that you're going to see, the pattern that you're going to see, is that we can just draw all of the previous electrons from the previous element. So I have my first electron is the same one as hydrogen. My second electron, because of Pauli exclusion principle, we must fill the lower level, or the lowest level orbitals first. So we can't move on to 2s because this one is not filled. Remember, Pauli exclusion principle says that we can have 2 electrons per orbital, right? They just must be in opposite directions. So, and Aufbau's principle says that we have to fill the lower level orbitals first. So this is why I can't move on to 2s. I have to fill up my 1s first. So Pauli exclusion principle says they must be in opposite directions. I'm almost done. I have to write how many electrons are in here, which is 2. There, my diagram, my electron configuration diagram is done. My longhand will be 1s2. That is the electron configuration longhand and the diagram for helium. Let's look at lithium. Lithium is number 3 on the periodic table. So we now have 3 electrons that we need to place. Well, as I stated, we're going to place the first 2 the same as we did for helium. 1, 2. So I have to write 2 here. But now we have a 3rd electron. So where does this 3rd electron go? I cannot put the 3rd electron in here. Why can't I put that in there? Think about that. I can't put that 3rd electron in there because Pauli exclusion principle says that only the maximum we can have per orbital is 2 electrons. So I have to move on to my next energy level. If I look here at this diagram, I've already filled this one up. So this one is filled, right? So now I go to the next energy level. That's 2s. Okay, so now I'm going to start filling my 2s energy level. So to do that, I will draw 2s, and I only have 1 electron left, and it has to go first in the upward direction. So there we go, and I write 1 here. So that is the diagram. The diagram is complete. To write the longhand, I'm going to write 1s2 from here, and then I'm going to write 2s1. There we go, and that's from here. That describes exactly where the electrons are in lithium. I'm going to go through the rest of these and then come back and do the shorthands, okay? So we're coming back to the shorthand just in a minute. Let me put this up here. Okay. Now I'm on beryllium. Beryllium is number 4 on the periodic table, so it has 4 electrons that I need to place. Hopefully you're starting to maybe see a pattern. So my first electrons, 1, 2, they're going to go in the 1s, and there's 2 electrons there. It's filled. Then I'm going to go to my 2s, just like above with lithium. And there's my 3rd one, just like with lithium, but I have 4 for beryllium. So where will the 4th one go? The 4th one will go in the opposite direction to completely fill up that energy level. And I write 2 there because there are 2 electrons in the 2s sublevel. So my longhand is going to be 1s2, 2s2. All right? All right, for boron, boron has 5 electrons. So I'm going to place the first 4 exactly as I have placed them above in beryllium. But now I have 1 more electron. So where am I going to put this electron? Aufbau's principle states that we fill the electrons from lowest energy level to highest. So we've already filled that one. We just filled that one. So now we need to go to 2p. All right? So there's a trick for this. I'm going to bring up a picture here. Okay. So if we look at this periodic table that I just brought up here, if we look at this, this is hydrogen, right? Let me erase this stuff so it's not in the way. I have hydrogen here and hydrogen here. This is 1s. This is 1s, right? 1s1. 1s1. Helium here is 1s2, right? And if you look at this, it's 1s. The 2s block covers lithium and beryllium. We have the final, how do I explain that? You don't know what valence electrons are yet. The last electron is in the 2s here, where lithium is. And the last electron for beryllium, the 4th placed electron, is also in the 2s. So this is the 2s block. Sodium and magnesium, 3s, 4s, 5s, etc., etc. Then we get over to boron, where we are at now, number 5, right? So all of this is called the p block. So the last electron that you're going to place is going to be in the p block in these. This is the d block, so this is where we introduce the d orbitals, and then these bottom 2, these down here, the these two, so I guess you don't know the name of those yet. Those two are the F block. We're not going to worry about the F block, but we do need to know the P and the D blocks. Okay? So the reason I'm showing you that is maybe, I hope that helps you understand where we're going to go from here. It kind of helps explain this diagram a little bit better, why we have this energy level, and then we go from 1s to 2s to 2p to 3s to 3p to 4s to 3d. So hopefully this explains that a little bit better for you, or you can at least see it a little better. So keep this in mind while I'm continuing to draw our electron diagrams or configurations. Okay, so we're on boron. We have 4 electrons placed so far, and we have 5 total electrons, so we need to place our final electron somewhere. Well, if you look here, we've filled this one, we've filled this one, so now we need to go to the 2p block, or 2p sublevel. So remember I told you that we draw these all connected. We're not going to draw them split up. We're going to draw them as 3 connected orbitals. And this is the 2p orbital. And maybe that's confusing, but it kind of lines up. See, like we have 1s here, and then 2s and 2p here. The place where it gets a little funky is when we go 3 and then 3d. That's confusing, but I'll get to that in a minute when I get down that low. Okay, so we're in the 2p block. All right, so Hund's rule states that we must place our electrons pointing upward first also. So there we go. And we have to put them in order, right? I can't put them over here. I can't put it over here. The first place that it goes is in the first orbital pointing up. So I would write a 1 there. Okay? So my longhand for this then, I'm going to have to scoot this over, aren't I? Yes, I am. All right, my longhand for boron is going to be 1s2, 2s2, 2p1. Okay? All right, now I'm on carbon. Carbon is number 6. So we have 6 electrons that we need to place. In our 1s, we're going to have 1, 2. Then we're going to move to our 2s. We're going to have 3, 4. Then we're going to move to our 2p orbital, because that's the next one in the energy level chart. It's the next highest energy level. So here we're going to have 5. And this is where Hund's rule comes into play. Hund's rule states that we want the electrons to occupy orbitals in a way to maximize the number of electrons with the same spin. So what that means is we want, when we're filling these orbitals, we want them to be, as many electrons to be facing the same direction as possible. So I'm not going to it is not correct to put the electron here. That's wrong. It is not correct to put the electron here. That is also wrong because of the way that we fill these. So it must go right there. Okay? So that is our 6th electron. So we write 2p2. Okay? So our longhand is 1s2, 2s2, 2p2. Okay? All right. Now we're on nitrogen. Let's scoot this down a little bit. Okay. Now we're on nitrogen. Nitrogen has 7 electrons. 1, 2 in the... Whoops, I forgot to write the numbers there above for carbon. And then we go to our 2s, 3 electrons, 4 electrons. And we'll go to our 2p. All right, this is going to be the same as carbon. 5 electrons, 6 electrons. Where will the 7th electron go? Will it go here? No. Will it go here? No. It must go here because Hund's rule says we want to maximize the number of electrons that are spinning in the same direction. You can think about this as kind of a balancing act. When we balance, like when electrons are spinning in the clockwise direction and the counterclockwise direction, that will kind of cancel out and balance each other. But if we have them all going in the same direction, that's even better to start. If we don't have, it's better to not throw in this opposite direction spin than it's better to have them all going in the same direction to start, right? Like this is more stable than having one electron, an extra electron, where did I draw that one last? If it was spinning this way, if it was spinning in the counterclockwise direction, then you have two, that just looks ugly also. You have two going in the clockwise direction, one going in the counterclockwise direction. It's much more stable and harmonious and nice if they're all going in the same direction, right? You can think of this as like, there's no chance, when you throw in a counterclockwise electron, okay? So I have a clockwise, right now, let's just say we have two electrons. I have one electron spinning in the clockwise direction, and I'm going to throw in this other electron that's spinning in the, I always do this wrong. It's spinning in the counterclockwise direction. So this doesn't happen. They're not going to collide, but it does increase your chances of them colliding. Now they have a chance to collide, right? Like it won't happen because they don't want to be near each other. However, if you're going in opposite directions, they could collide right here, right? So that's just increasing the chaos when we throw in these electrons spinning in opposite directions. So Hund's rule says we want them all to be spinning in the same direction first, then we'll sprinkle in the chaos casually as we must, okay? So this is nitrogen. We forgot the 3 there for nitrogen. So that's nitrogen's electron configuration diagram. To write this longhand, I'll write 1s2, 2s2, 2p3. Oxygen has 8 electrons. 1, 2 in the 1s. Then we have 3, 4, in the 2s. And then we're going to have to place the last ones in the 2p. So, same as nitrogen, I'm going to fill them all with the same direction first. So I have 7 here. I have 2, 4, 5, 6, 7 electrons. I have one more to place. Now, Hund's rule says we're going to go back to the beginning here, this first orbital, and I'm going to place that electron in the counterclockwise direction in that first orbital in the p sublevel. So I now have p4. So I have 1s2, 2s2, 2p4. All right. Finally, we have fluorine. Oops. For that, it has 9 electrons. All right. So we're going to do we're on 5. That's number 5 because we already have placed 4 electrons before this. So that's number 5, number 6, number 7, number 8, and number 9. So we have 5 electrons here. My electron longhand, and my configuration longhand is 1s2, 2s2, 2p5. All right. Neon is number 10. I'm going to also write neon here. Neon, because I need neon to explain the last part of Hund's rule. Neon has 10 electrons. So 2 electrons in the 1s, 3, 4 electrons in the 2s, and then we have to place the last 6 electrons in the 2p. They're going to go 1, 2, 3, 4, 5, 6. That is a total of 10 electrons if you count all the arrows, or if you add up all these numbers, we can also find the number of electrons that way. So this is 10 electrons, so we're good. Now we can write our longhand. So our longhand is going to be 1s2, 2s2, 2p6. All right. How much time? All right, it's already been 25-ish minutes, so we're going to talk about the last part of Hund's rule here. We need to do that's what we're gonna talk about Hund's rule, what I mean by these 3 things here, and then we're gonna stop. Okay, so stability. the reason that Hund's rule exists is because we have this idea of stability in our electron diagrams. So we have this thing called stability, and the most stable is a completely filled, or just a filled. I don't usually say completely filled. I just say a filled filled sublevel. So filled, we have partially filled. Excuse me, we have half filled. Exactly 1/2 filled. And then we have partially, or a partially filled. Okay, so what do I mean by that? What I mean is when we're looking at this, we need to look at the last electrons. The electrons, the last electrons that we put into the diagram that we're drawing. So we're going to look at our electron diagrams here. We're going to look at these in order to understand these concepts, these three concepts here. All right, so our first one here is hydrogen. This is exactly half filled. This is a half filled sublevel because in our 1s orbital, we can fit 2 electrons. However, we have 1 electron here. 1 divided by 2 is exactly 50%, half, right? So that's half filled. Helium has a filled sublevel. We cannot fit any more electrons in there, right? Then we look at lithium. So lithium, we're only looking at its last sublevel, the very last one, okay? So we ignore this one. Our last sublevel level is the 2s sublevel, right? So this is it half filled or is it filled? It's half filled. Okay? Then we look at beryllium, and we're looking only at where the last electrons were placed, only at the last sublevel that we were working on. So we're ignoring that one because it's completely filled. Just the last one. This one is filled. All right. I said boron, I meant beryllium, sorry. Okay, now we're on boron. So we're going to look at just the last sublevel. So this one is completely filled. This one is completely filled. We're just going to look at the last sublevel. This one, is it half filled? No. Half filled would be like down here, like nitrogen. This one is half filled, right? This is half filled because I have 3 electrons total, but 6 electrons can fit. So this one is half filled, but what about, geez, Ailey is unhappy, sorry. What about boron? Boron, it's not filled, it's not half filled, therefore it's what's called partially filled. It's partially filled. All right? Same thing with carbon. It's not half filled, right? Total, it can hold 6, the 2p can hold 6 electrons, but it only has 2. So that's not half. So that means that it's partially filled. Then we get to nitrogen. I told you since there's 50% of the electrons, 50% of the electrons that can fit are there, then that is half filled. All right, what about oxygen? Is it partially, half, or fully filled? It's not fully filled because I can still fit 2 more electrons in there. It's not half filled because it has more than 3. Therefore, it must be partially filled. Same with fluorine. We don't have a fully filled. We don't have a half filled. Therefore, we have a partially filled. Then we get to neon. Neon is fully filled. It's a filled sublevel, okay? Because it has the maximum amount of electrons that can fit are there, okay? All right, so all of these based on, we base stability of the atom. We look at the stability of the atom, how stable it is, how much energy it has total, based on whether it's a filled sublevel, a half-filled sublevel, or a partially filled sublevel. Okay? So, the most stable is filled. Electrons are most happy when everybody is canceled out, right? Remember I told you, look at neon here, this one. Remember I told you that when we have electrons going in opposite directions, they kind of cancel each other out. We have a clockwise and a counterclockwise, right? We create, actually it's creating a magnetic field is what it's doing. And it's very happy. It makes the I sound like Donald Trump. We're very happy. It makes the electrons very happy. That was a terrible Trump, but you know, that does sound like something he would say. We're very happy. The electrons are very happy when they have two, they're occupying an orbital with someone going in the opposite direction. It's just called balance. You're going to see it over and over again in science, okay? So this balance makes something like an atom of neon very happy. It's very stable. It's not very reactive at all. It's very low energy, very chill, right? It's got all of its electrons, you know, man. It's just like super chill and stable, dude. This is a filled. This is filled. It's the most stable. We have half filled. So something like nitrogen is half filled, right? So this one, there's at least balance, right? We're half. I mean, it makes sense. It just makes sense, I think, common sense, that if something is exactly half filled, that is more harmonic and more harmonious than something that only has, like, that is partially filled like this, right? We have exactly half of the electrons. They're all going in the same direction, but they're all, remember this picture? Oh no. They're all going in the same direction, clockwise, but they're all in different orientations in space. They're all occupying different, this is on the x-axis, this one's on the y-axis, this one's on the z-axis. So they're all going the same direction, and they're not even occupying the same place in space. So this is medium, I don't know it's medium stability, middle stability, okay? Then we have partially filled, and of course that will be our least stable electron configuration. So something like boron. This is a partially filled configuration. Boron is not happy. It's like it's off balance. It has only one electron spinning in the the clockwise direction in the p. We'll say this is, remember, it's px, py, and pz. Each one of them is px, py, pz. So it has one electron counterclockwise in the px, but it has a lot of empty space all around it. So it's not as happy as when we have something like a half filled, or even better, a fully filled, right? Same thing with, what's another partial here? Oxygen here. Oxygen, ooh, this one is even, it just looks yucky, right? Like, this looks like it would be unstable. I don't even know, even if you don't understand what unstable means, it still just looks like, yeah, I would choose that one. It doesn't look super happy. Because it has 3 in the clockwise direction and 1 random one here in the counterclockwise direction. It's partially filled. It's the least stable. It's less stable than half filled, and half filled is less stable than fully filled, like beryllium up here. Okay? All right, last thing I'm going to leave you with is you're going to find that we have this group of... Let me make this periodic table bigger here. All right. In our periodic... Nope, can't do it like that. I'll zoom in this way. In our periodic table, group 7A, 8A. Remember, this is 7A. This is 6A, 5A, 4A, 3A. These are all the B groups. And then we have 2A and 1A. Right? Okay, so group 8A, this purple group here, this group is the happiest, best, most chill group. It is going to have every single, I don't know about the last one actually, that's not really technically, it is. But this group, screw it, the whole thing. This group is called the noble gases. Noble gases. The noble gas group, okay? all of those elements are super stable. They do not react with anybody else. They don't even react with themselves. They don't want to react. They are like the world's best, strong, independent woman, right? They don't need no man. They don't need no one else. Only themselves. They exist as individual atoms. The reason for that, why they're so stable, look, this is one of them. This is the first one. This is the first noble gas, helium. The second noble gas is neon, down here. What do you see is similar between those two? They are both filled. They both have filled electron configurations. They have all the electrons they need. They're not missing anything. They are super stable. So we're going to see that all of the noble gases have all of their electrons. They're super happy, super content. Okay? So that's important because we're going to need to understand what noble gases are tomorrow, or Friday, when I start giving you information about, or when we start learning how to write the shorthand. Okay? We're going to need to write those noble gases. We need to understand at least the noble gases. Okay, so that's where we'll stop today. You have an assignment that's due today by 7 p.m. If you need more time, you need to obviously talk to me before 6:57 this evening. You should talk to me hopefully as soon as you're done watching this video, or by 5 even. Talk to me and let me know what's going on. That's not an excuse. I'll need a parent excuse. If you're having internet problems, I will obviously need to have a parent note. But if you just have questions or something, please reach out to me and let me know. The questions are simple and they should take 20 minutes to do. Please let me know if you have any questions. Thank you.